Welcome to Advanced Quantum Chemistry and my fifth lecture on Hartree-Fock theory. The topic is the Hartree-Fock Hamiltonian. Two of the characteristics of Hartree-Fock theory are that the Hartree-Fock-Slater determinant, which is the Slater determinant built from the n spin orbitals with the lowest orbital energies, that this Slater determinant is not an eigenfunction of the Hamiltonian of the system. Now this should not be a surprise, because if this Slater determinant would be an eigenfunction to the Hamiltonian, then the Hartree-Fock wave function would be the exact solution to the Schrödinger equation, and Hartree-Fock theory would be just solving the Schrödinger equation exactly. But we all know that Hartree-Fock theory is an approximation, so therefore the Hartree-Fock-Slater determinant cannot be an eigenfunction to the Hamiltonian. The second point is, as we discussed earlier, that the Hartree-Fock energy is not the same as the sum of the orbital energies, and the physical explanation for that is that the orbital energies include the one orbital energy, for example for the spin orbital I, includes the interaction with the electrons in all other spin orbitals. And if we sum then over all spin orbitals, we count this electron-electron repulsion interaction twice. And they cannot be correct, but the Hartree-Fock energy only counts it one. So the question is, since the Hartree-Fock-Slater determinant is not an eigenfunction of the Hamiltonian, is there an operator for which the Hartree-Fock-Slater determinant would be an eigenfunction? And this is sort of an approximate operator for the system. And the answer is yes, there is such an operator, and we call it the Hartree-Fock Hamiltonian, to distinguish it from the Hamiltonian of the system. And this Hartree-Fock Hamiltonian, HF Hartree-Fock, is just the sum of the Fock operators for all the electrons. So if we sum the Fock operator for all the electrons, we get the Hartree-Fock Hamiltonian. And for all the Slater determinants, which we can make from the eigenfunctions of the Fock operator, which mean all our spin orbitals, which are eigenfunctions of the Fock operator, meaning all the spin orbitals which we get from solving the Hartree-Fock equations, all those Slater determinants are going to be eigenfunctions of the Hartree-Fock Hamiltonian. For Hartree-Fock theory, this is actually not really relevant, but we will come back to that later when we talk about correlated wave function methods, in particular about Müller-Blessed perturbation theory, where we will come back to this and where it becomes important.